Hello, this is Mrs. Schroeder. We are here today to talk about equilibrium and stress. We're going to learn something called LeChatelier's principle and learn how to apply this, whether it's a forward or reverse reaction. What happens when that reaction is stressed? So stress is just another word for saying something causes a change to a system at equilibrium. And chemical equilibrium will respond to three kinds of stresses. One is change in the concentration. A second one is change in temperature, and a third type of stress is change in pressure of the system. All of those create stress on the system. They'll affect the rates of the forward or the reverse reaction so that they are no longer equal at that point in time until the system reaches a new equilibrium. So LeChatelier's principle states that when a system at equilibrium is disturbed, it will adjust to reduce that change. Whenever you're trying to apply LeChatelier's principle, you want to look and say, what is the stress causing? Is it on the forward side or the reactant side? So I would know which way it's going to respond. When I increase the concentration of the product or reactant, it will respond by going the reverse way. It wants to reduce it. So if I increase it, it tries to reduce it, tries to remove it. Okay, that's how it's going to react. It wants to remove. If the reactant is added, it shifts to the right. If a product is added, it's going to shift to the left. And that's what we'll say. We'll talk about things as shifting left or shifting right, if it favors the forward or the reverse reaction. I can also remove things. Okay, so if one of the products is a gas, I can start removing that gas, and I'll drive the reaction to completion, because as I remove it, I'm going to try to make more of it, because I want to have that KEQ. I want KEQ to be constant. And we'll go over some examples and demonstrations in class. Temperature is also stress. Now KEQ is dependent on temperature. It does change with temperature, but it changes also because I have reactions that either give off or take in energy. If I have an exothermic reaction, I'm going to write energy on the product side. So now you can see if I increase this, I'm going to shift the reaction away from that energy increase. I'm going to shift the reaction left. I want to go away from that. So if I have an exothermic reaction and I increase the energy or increase the heat temperature, I'm going to shift it in favor of the reactants now. Endothermic reactions act just the opposite. They take in energy, which I've written now on the reactant side. So if I increase the temperature, I'm going to react in a way to reduce that energy, which will shift it in favor of the products. Again, stress is trying to reduce the stress. And again, some demonstrations for class. Pressure is the third stress. Now, pressure only affects gases. It does not affect solids or liquids. So if I have a gas system, pressure will be a stress to it. If it's not a gas in the system at all, there's no stress when I change the pressure. So pressure will favor the one that produces fewer gas molecules. Whichever side has fewer gas molecules is the side that will be favored when I increase pressure. So for example, I would look at this. It's a gas phase reaction. So I see 3 gas molecules, or all my reactions and products are all in the gas phase. Which side has fewer gas molecules? Well, I have 2 gas molecules here, and I have 2 plus 1, so 3 gas on the reactant side. So, or on the product side has fewer gas molecules. So if I increase the pressure of the system, I'm going to shift it away from the 3 towards the 2. I'm going to shift it back towards the reactants. So I'm going to shift it towards the reactants. I might also say the reverse. Or I could say I'm going to shift left. All 3 of those are equivalent ways of saying that I'm going this direction. the direction the arrow is going. Because I have 3 gas on this side and 2 gas on this side, I'm trying to go from 3 to 2. Okay, so remember that pressure changes goes towards whichever side has fewer gas. We'll talk about reviewing that. The last thing I'll talk about is something called the common ion effect. This is essentially change in the concentration. So we had an example problem in class when we were talking about solubility, where we had copper chloride in water and copper chloride in seawater. And we said solubility differed. In regular water, it was 1 times 10 to the negative third, and in seawater, it was 2.2 times 10 to the negative 6. It was much less soluble in seawater. And the question is why? Well, if the KSP is 1.2 times 10 to the negative 6th, it must remain constant. So if I increase this, it's called a common ion. I've increased it by adding something else that has chlorine in it. Sodium chloride, calcium chloride, something else that would have chlorine in it. And that reduces the solubility now because of that common ion. We call it again the common ion effect. Essentially, again, just changing the concentration of one of the ions in solution changes its solubility. So we'll do some demonstrations. We're going to do a practice with an equilibrium reaction and causing some stresses. But there are some practical uses to LeChatelier's principle. The most common of these is the ammonia reaction. If I have nitrogen and hydrogen, it goes to ammonia. These are all gas phase reactions. Heat is given off. I want you to think about how, if you could, what kind of shifts would you do to cause more ammonia to be made? So think about LeChatelier's principle and see if you can answer this question in class when we meet again.